All right. So I know that the notes I gave you for Friday also talked about the standard form of an angle. And the reason I gave you that packet was I had to give you guys something now. I was all done with all the exponential and logarithm stuff. I didn't want to give you any more of that. So the next thing was we're going to do trig. So let's look at angles because that's what trig's all about. Angles, angles, angles. And the standard form is you have your XY plane. And you always want to think about your angle having two legs. Because in geometry, you learn that if that's an angle, then these two things are called legs. Remember that? Legs of an angle. And the legs can go together or they can go apart. So I want you to envision that one of your legs is always laying on the x-axis, the positive x's. That's called an initial side. Initial. Because that's where, if you had both legs laying there like this, let me change the color so you can see it, then they're both at 0 degrees. You haven't opened up. So what happens is one of those legs have to open up to the left. And I think I typed that in on one of the sets of notes. As the leg opens up to the left, like this one did, this leg now becomes the terminal side. Terminal means where does it end? And you're going to find out that these 4 squares that are created by your XY plane, this is called quadrant 1. It's your right hand going up in the air, 1. And you go over, this becomes quadrant 2. This becomes quadrant 3. And if you were a cheerleader, and we have one in here, they could probably do a really good job at doing quadrant 1, quadrant 2, quadrant 3, quadrant 4. You know, little pom-poms, you can imagine that. Quadrant 4. So the angles have to open up and create a measure. Now, you already know that there's 90 degrees in a right angle. Is that correct? So if you just opened up to here, that's a 90-degree angle. If you go a little more than that, then obviously you're approaching 180 degrees. Because over here is 180 degrees, that straight line, 180 degrees. So that's standard form always starts at the 0 degrees over here. And then we measure going up and over, okay? And yes, I saw the picture on the board. Mr. Mendoza, he decided to look at the notes that I gave, and he was drawing some angles up there. I thought he was actually teaching a class. I asked him yesterday, which class did you present that to? He said, oh, nobody. I just wrote it in the morning in case anybody wanted to look at it. I said, oh, okay. It was nice what he wrote.
Sir, what does the red say of the word under?
Initial.
Oh, okay.
It's an initial side, and maybe they'll bring up the words in here, but I didn't pre-read these questions, so we'll see.
That's like where it starts?
Yeah, it's where both legs start, and then one's going to open up, okay? You never have them both opening, only the one. One's initial, it stays there at 0, and the other one always opens around. It could go all the way around 3 or 4 times. It doesn't matter. It can be bigger than 360 degrees. For those of you who are skateboarders, you know that a 360 meant you spun the whole board around all the way around, if you're really good at that stuff. And a 180 was you changed directions. 180 because you changed the direction. I was going this way, now I'm going this way. That's a 180-degree turn. You know, so you've heard those terms before. Okay, an angle in the coordinate plane is in standard form when the vertex, I didn't mention that, vertex is right here that connects the two legs together. Why isn't it writing? It's writing there. There it is. So right here, that dot here would be the vertex of the angle. So the vertex is always at 0, 0. So it says here the vertex is on the origin, that's 0, 0. And one ray, remember the legs are actually the geometric ray. A ray has an initial start and it moves in one direction forever. That's a ray. That's not a line, that's a ray. And it lies on the positive x-axis. One lies positive x-axis. That's this right here, positive x-axis. The ray on the axis is called, oh, there it is. The ray that stays on that x-axis is called the initial. Pretty sure she probably used the word ray because she brought up the ray. So I'll put the word ray, but I'm going to put it in parentheses, a leg. The leg of an angle. Maybe she doesn't like to use the word leg, but they've been called legs of an angle forever. Then the other ray is called the terminal, because that's where the angle stops. That's where the measurement stops. Terminal ray, but I'm still going to call it leg because I have no idea what she wrote. Counterclockwise, this is a tough word for you guys today. Most of you haven't paid attention to a clock that goes in a direction because we're so used to a digital clock. There's kids in elementary who can't tell time on a regular clock like they used to. It used to be part of your class. You'd have to learn how to tell time on a clock. I don't think they do it anymore. I don't think they do, but maybe they do. I'll have to ask my daughter if my little grandkids are still learning to read the hands of a clock. But counterclockwise, I hope somebody knows that normally this was 12 o'clock and this is 6 o'clock and this was 3 and this is 9. So if you have two hands of a clock, or at least even looking at one hand, if I started here and I went this way, would that be clockwise?
No, yeah.
Yes, that's clockwise, because 12, 1, 2, 3, 4, 5. If the hand went all the way and stopped here and your hand was here, then you know it's 5, 6, 7. So that's clockwise. So maybe make a note of yourself and say, this is clockwise. And if you go the other way, it's against the clock. So it's counterclockwise. Clockwise is the way the clock is from 1 o'clock to 6. That's clockwise. And if you're going against the clock, you're trying to make time go backwards, that would be counterclockwise.
So counterclockwise is like going like this?
Well, you're backwards. So which way did you go?
Like,
Okay.
clockwise.
Do you know where 1 o'clock is on a clock?
Yeah, like if this is the clock, then
Yeah.
clockwise is going this way, then
Yes.
clockwise is going the other way, right?
Now, clockwise goes the same way as the clock. You're going to go, if you're going this way, your clock would go 1 o'clock, 2 o'clock, 3 o'clock. That would be your clockwise.
And then counterclockwise is the
Would be the
opposite.
other way around. Yeah. Who would have thought that would even be back in the old days, I never would have to even mention it. But I was looking at that, I said, I bet you some of you have not even really looked at a clock with hands of a clock. If you buy one of those clocks, it's usually for decoration. Because even your phone, it's all digital. So, wow, interesting when you think about how things have changed. Counterclockwise will result in a negative. Let me look. Hold on, let me look. This is counterclockwise, right? That was opposite of the clock? So yeah, that would be counterclockwise would be a negative answer. Okay. I had to actually look at it myself. Negative. Degree measure. I got to look again. Make sure I'm talking. Which way did I go? Let me do it again because I already forgot which way I went. Come on, erase. All right. Let me pretend that's a clock. Let me draw the clock. Here's the clock. Okay. So if I had a hand here at 3 o'clock, and the hand, which way would the hand normally go? It ticks down this way, right? 4, 5, 6, right? So that's clockwise. So I was actually wrong. Counterclockwise is positive. I was wrong. I knew if I looked at the picture better, I would correct myself.
Sir,
Yes.
may I use the restroom?
Yes. Positive if it's, and the reason is the angles, as I said, we start both legs down here, and then one of the legs opens up this way. So it opens up here. That's a positive angle. So that's counterclockwise. That goes against the clock. That I'm going against the clock because I'm moving this way, and that's counterclockwise. It's pushing the hands. If you go backwards in time. Oh, I forgot to put the E. E. Clockwise will give us the negative. It's too bad that we're just not used to looking at clocks. We're not either. We get lazy too. So why do I look at a clock for? Actually, I don't know if you do this. Sometimes I'm just sitting in the couch and I just ask Siri what time it is, or I ask Alexa what time it is. You ever do that? No? What's that? Is that a bad thing?
No, I don't know. I think it's just like repetitive.
Uh,
I don't have it. I just look at the time on the phone.
Oh, okay. Well, I don't. Once I'm home, my phone gets plugged in. I don't try not to look at it. The most common unit of measuring for an angle is in degrees. Most common measurement for angles is the degree. Okay, you see what they have, that little symbol in parentheses? It's a little circle. You actually have it, I think you have it on the keyboard, maybe, where you can raise a circle up. And you've seen 90 degrees. That's how you would write it out, 90 degrees. That's the most common. That's what you learned in your geometry class. You did degrees, okay? A degree is equivalent to, so my question is, how many degrees are in a circle? So 1 degree is 1/360th of a full rotation. So you'd have to, if your second hand could only move 1 degree, you would have to have 360 movements before it went all the way around. So that means a minute, there's 60 minutes in the clock. You would have to have a 60 times 6. Every minute would have to be a degree, and would have 6 degrees in it. Every minute would have 6 degrees. So it's not very fast. I don't know how many seconds that would be. What's 60 seconds divided by 6? 10 seconds? So every 10 seconds the hand would move a degree. Every 10 seconds. That'd be a pretty cool clock. To actually see it move every 10 seconds a little tiny bit. Every 10 seconds a little tiny bit. And by the time it went all the way around, it went 360 times. So we're going to draw a couple angles here. And that's what I wanted you to do on Friday. I hope you did draw some angles. You don't have to be exact. We know that between 0 degrees and up here is 90. So I would just ask you to use some common sense. What would be half of this measurement for fun?
30?
Nope, that would be a third. 30, 60, 90.
So the middle 60?
Well, the middle 60? Well, what's half? How many degrees is half of 90? Did somebody whisper it? How many? 45 degrees. So this would be 45 degrees. It's half. So you know that you'd have to go more than 45 to get to the 65. So you don't have to be perfect. You just would have to say, okay, let me open up this angle till I get past the halfway mark there. And I'm going to say that's close enough. And I would call that 65 degrees. You don't have to be perfect. If I wanted you to be perfect, we would get out the compass and the protractors and we would do it like you did in geometry. Hopefully you did it in geometry. A lot of geometry teachers don't pull that stuff out anymore. They just say, look at the pictures. We all get lazy. Now 320. What was it all the way around? 360. Do you know what it is if I stop right here? How many would that be? 270. Well, if this is 270 and this is 360, I need to be somewhere probably between those two numbers, but closer to 360. Would you agree? Well, Mickey agrees. So I'm going to draw it. And again, it doesn't have to be perfect. I'm going to stop right there and call that my angle. All the way around here is 320 degrees. Now, you're going to learn something that we don't really care about that angle. We really care about this angle right here. That's called a reference angle. But the big angle is 360. I didn't write it right. 320. That's close enough to 320. Okay, 415. What's wrong with 415? It's bigger than 360. Yeah, look at. That means if I go all the way around once, I've already done 360 degrees, haven't I? But I need 415. So how many more degrees do I need? It's okay if you have to do your scratch work and say 415, take away 360. How many is that? 55 degrees more. Well, you already know that halfway was 45, right? I'll just do a little more than halfway. How's that? There it is. So I'm going to do this. All the way around once and a little more. That would be 415 degrees. But in reality, we won't really use the 415. We're only going to use this amount right here, the 55. The 55 is more important to me than 415. Just keep that in mind. All right. Okay, there's a negative angle. So I open down, don't I? Both of my legs still start here, right? But I open down 140. So I don't know where it is. So just help me out. How far have I gone right now? A negative 90. Negative 90. How many have I gone if I go all the way to here? How much? A negative 180? Is that too far? I need to come back 40 degrees, don't I? So would you agree with me that a better answer would have been all the way to about here?
Like somewhere in the middle.
Yeah. And I always draw the other angle, the other ray, or the other leg. I always draw it from the 0, 0. So there you go. I'm going to draw that as my negative 140. In reality, you don't need to have to do 1,000 of these. You just need to do a few to understand the idea. And then you'll get better in trig. In reality, we don't really use those big angles. Only if we're representing something dumb like your car is rolling down the road and it makes 50 revolutions every minute. How many angles have you traveled in an hour? Well, that's, 50 revolutions times the 360 degrees, because every time it went around, it made a revolution of 360 degrees. Then you traveled for an hour, so you could just multiply it by another 60, and bingo, this gigantic number that nobody cares about in reality. It's just one of those problems that math teachers make us do to make us think about angle measure. All right, negative 15 degrees. Again, we're going to be opening from this leg here. We're going to open down. If I open this far, it's probably too many. Because that would be like a negative 45 degrees. That's too many. I need to come back a little bit. Maybe there? I'm just guessing because I'm not measuring it for real. So I'm just going to go down this way and then connect that. That to me would be a negative 15 degrees, more or less. Now we're doing another negative. And if I start with my initial side there and I start opening down, that's a negative 90. That's a negative 180. Negative 180. How many's left? 210. Take away 180 is about how much? 30. I need 30 more degrees. And I like what Mia said earlier about 30 degrees because there's 30 and 60 and 90. If you divide that into 3. So I'm just going to go up to this one right here and draw my angle from the origin. Draw that and go straight out like that. So there's that side opening down this way, opening this way, keep going until I get there. And to me, that's enough. I mean, you don't have to be a genius at this. It's just a little bit of thinking. Now, you haven't even got comfortable with degrees right now, but they assume that you did degrees in geometry. You're supposed to have done a little bit of trig. And here's proof. You have heard of Chief Sokotoa? Nobody heard of Chief Sokotoa? That's scary. Your geometry teacher didn't, did they teach you the sin? The cos?
Maybe. I don't remember.
Maybe? Tan for tangent?
Oh, yeah.
My teacher's like for geometry.
So then you should have learned Sokotoa when it came to a triangle. But if not, I guess I'll have to teach you when I get there. So let's see what we're doing about radians. Radians is the measurement that is required for calculus. In calculus, we never talk about angles being in degrees. So that's the first time that they get exposed to it. Some of us never used to teach radians in regular pre-cal. We just stay with degrees for now. But the curriculum has changed. Even the AP pre-cal, it's in pure radians. So the teacher has to do a little bit of degrees just to get you going here. So now, a radian is a unit of angle measure based on the length, arc length. That is true, arc length. An arc length is a distance like from here to here. That's an arc length. That distance on a circle is an arc length. And that is true. Radians have to do with arc lengths. And so what we have learned, let's see what else he said. One rotation is defined as a measure of the angle formed when the radius is equivalent to the arc length of the intercepted circle. All right. If I just arbitrarily tell you that I'm going to draw a circle. Here's the center. If I start drawing a circle, and I end right here, The intercepted arc means the angles from this point all the way around to this point. You want to take a guess at what the degree measure was? 180. All the way around?
360.
It's 360 degrees. Now, let me ask you a question. Geometry. If I asked you, find the distance around this circle, what word was that in geometry? The distance around the circle. The diameter is the distance between the center. That's the radius. And this is another radius, so together that's called the diameter. Diameter cuts the circle in half. I want to know what is it called when I want to measure the distance around. All right, let me ask you another question. What's the term when I want to find the amount of space that is inside the circle? And okay, you think this is the perimeter, the amount of space I'm taking up? Is that perimeter?
Area?
That's area. Now, you said perimeter. Isn't perimeter the distance around?
Because the perimeter is like the outside.
Okay. So now we're cooking with gas. If that's the perimeter, was there a special name for a circle? No. A sphere is a three-dimensional circle, like a basketball.
Circular object.
Thank you. Circumference. You had circumference in your early classes, and you had area. And just for fun, we did already talk about this distance being the radius. What was the area formula? What is the area of a circle? You forgot?
360.
No. The formula. Pi
Oh, like
times
point.
r squared. Pi r squared. You don't remember that? Okay, well then I bet if you don't remember that, you won't remember what circumference was.
Isn't like the C equals
Keep going.
like
2.
C isn't part of the thing, right?
C is the circumference, yes. 2
No, X not in it.
pi r.
Uh,
C is 2 pi r. Area is pi r squared. You didn't hear about the, now, I lived in Tennessee for a while, so I'm allowed to talk about southern people in the mountains. They called them hillbillies, and one of my favorite shows growing up was the Beverly Hillbillies. One of the sons was sent to college, and he came home, and Ma and Pa, they were called, were so excited to have their kid home and said, well, we don't even think school is that important. What'd you learn? And he said, well, Ma, I learned pi r squared. And the mother looked at the father and said, you see, we all know pies are round. Stupid college. Pi r squared. Okay, all right. Oh, you guys are a tough crowd. Anyway, this measurement around is the intercepted arc of that angle, because my angle opened all the way around, so the angle is the whole circle, and that circumference is 2 pi r. So it just so happens that I can actually tell you, let's see, 2 pi times the radius is 360 degrees. And if I use a radius of 1, then 360, I don't have to worry about this r. I can just say 360 degrees is equal to, I don't want that color. 2 pi, the word is radians. If the radius is 1, and that's what we always go by. Whatever radius we have, it's a 1 unit, whatever it is, we say 360 degrees is 2 pi radians. Radians doesn't have a symbol. It's the word radians. 180 degrees would be half of that measure. So what's half of 2 pi?
Wait, half of 2 pi?
What's half of 2 pi?
1 pi?
1 pi.
Oh, shit.
So it's pi radians. You see? Recall that the circumference of a circle is 2 pi r. That's what he wrote up here. So I did use that, 2 pi r. But I used the radius to be 1. Okay? So we're going to have to convert back and forth from degrees to measurements. So it's kind of simple. The reason he said, what's related to 180? Pi. So I can convert to radians very simply by taking my degree measure and just multiplying it by pi over 180. Why can I use pi over 180? Because pi radians is 180 degrees. This amount right here is just equal to 1. It's like saying 12 inches over 1 foot. Or flip it, 1 foot over 12 inches. It's the same unit. It's the same measurement, right? So basically it cancels out. If you want to go from radians, you flip it. You put the 180 degrees on top and the pi radians in the bottom. So what happens when you do this mathematics, this radians here cancels out the word radian here. So you're only left with 180 divided by pi. Actually becomes the number. Whatever the number of radians though. You still got to do the math. So we're going to have to go do the math. Let's see. Okay, so we're going to convert degrees to radians. So the ratio that, or the fraction, I want you to remember, there's 2 of them. You can say there's 180 degrees for every pi radians. And we don't have to use a symbol for radians. We just say pi, and it's understood to be radians. Or you could use the fraction pi radians over 180 degrees. We got that from the other page. We were looking at that. So when you're converting 60 degrees into radians, I have to pick one of those fractions to multiply by. And since I want to convert it to radians, I want to remove this degree symbol. So the best fraction to multiply by would be the one that has the 180 degrees in the bottom. So I'm going to put a pi over 180 degrees. The reason I want to do that is this degree symbol at the top will cancel the degree symbol at the bottom. So all you're left now is with 60 times the pi, and put a 1 under there if you want. So that's 60 times the pi over a 1 times 180. There's no degree symbol. Therefore, we know it's radians. So the pi stays as part of my answer. But now reduce 60 over 180. I think that turns into, let's see, if I was to say 60 goes into 61, 60 goes into 180 3 times, that would give you a pi over 3 radians. So 60 degrees is equal to pi over 3. It won't mean much until you see a whole bunch of these. Let's do another one. 160 degrees, again, I will multiply that by pi over 180 degrees. That forces the degrees to cancel. So I'm left with 160 times pi over 1 times 180. And so that reduces. The pi stays in the answer. And let's see, I don't know what it reduces to, so let me just cut them both in half. Let me say 160 turns into 80, 180 turns into 90, and I still have my pi. Oh wait, the zeros can cancel now. Divide both by a 10. So I'm going to say to you that 160 degrees is equal to 8 pi over 9 radians. I don't have to write the word radians. I don't have to write a symbol. If you want to write the word radians, you can. All right. I'm going to do one more. Then I'm going to move on because that'll be 3 of them. I'm going to take this 330 degrees over 1 and multiply it by pi over 180 degrees. Degrees is in the top, degrees is in the bottom. That means they cancel. That turns into 330 pi over 180. Well, I don't know how that reduces. Let me just say divide 330 by 10. That gets rid of that 0. Divide 180 by 10. That gets rid of that 0. So that turns into 33 pi over 18. Okay, I see what happens. I can now divide both by a 3. 11 pi over 6 radians. So let me be clear. What I had just done was 330 degrees is equal to 11 pi over 6. And I'll put the word radians for right now so I can show you that that's what it happens. But radians has no unit. So you don't have to write the word radians. You can just understand it to be 330 degrees equals to 11 pi over 6. And if I don't say anything, then you know it was radians. All right, enough. You can play with the other 3 on your own if you wish. Well, I'll do one more because this is a famous one. You're going to see this again. I'm positive. Multiply by a pi over 180 degrees. The 2 degrees symbols cancel. The negative is a negative angle, which, by the way, that's a negative 45 degree angle. So here's your leg, and it opens down 45 degrees. There it is. That's what that angle looks like. That's a negative 45 degrees. Equals to a negative 45 pi over 180. Now, how many 45s go into 180? I think it's 4 of them. How do I know that? I'm going to take 180 degrees, show you what I was thinking. Here's 180 degrees, that angle there. Here's a leg, there it is. So if I take 90 degrees and cut it in half, that's 45. That's another 45. That's another 45. That's another 45. So I know that turns into a negative pi over 4. Okay? Okay. I'll let you do number 11 on your own, 11 and 12, okay? Let's now convert radians to degrees. So obviously, if I'm looking at this angle, 5 pi over 18, you know it's in radians. Not because you see a pi, but because you don't see a degree symbol. So if I want to turn this in degrees, then I have to make sure my numerator has degrees in it. So I will multiply by 180 degrees over pi. Now, you may not think this is a coincidence, but it actually is. The fact that I have a pi on top and a pi on the bottom does cancel. Let me change that to a red here. So the pi's do cancel out. So now you are left with 5 times 180 degrees divided by 18. Now, I don't know how you're going to simplify this, but since I've done a million because I'm, almost 100 years old, 180 divided by 18 That's 10 up there. So I did some simplifying right away, and so I can now be confident that the answer is 5 times 10, 50 degrees. Okay, let me do another one. Obviously, this is in radians, so I need to make sure my degrees is in the numerator. 180 degrees over pi radians. And again, what a coincidence. The pi's cancel because I have a pi on top and a pi in the bottom. And I could do 11 times 180 degrees all over 9. But why don't we do some thinking and say to yourself, 9 goes into 18 twice. So that really turns into 11 times 20. That'd be a 220 degree angle. Well, let's do one more. And I'll look to see if I want to do any others. Converting radians into degrees. No symbol, the degree symbol. So NA, it has no symbol. So I will multiply this by the fraction of 180 degrees over pi. Just so happens the pi's cancel, which happens all the time, guys. But you need to understand that I could give you a radian that doesn't have the letter pi in it. Let me see, is there any down here? I don't think she would have done that to you. That'd be a dirty trick. I may do it to you someday just because. Try to trick you. But this time there is 2 pi's, so they cancel. And let me see if I can simplify ahead of time. 3 doesn't go into 7, but 3 goes into 18 6 times. So that becomes a 60. So that turns into 7 times 60 degrees over nothing, because the 3 canceled, the pi canceled. So 7 times 6 is 42 degrees. Do I want to do any more of those? Let me do this one. This is a famous one. By the way, it's a negative angle. So don't be surprised if this angle opens clockwise and forms an angle down here, okay? Don't be surprised. So here goes my conversion. Times 180 degrees over pi radians. And the gods are smiling down on us because the pi's cancel. And the 6 goes into 180 30 times, if you want to be honest, 30 degrees. So I'm left with a negative 30 degrees. Well, hello. It's almost like I knew what the answer was going to be, because that's about 30-degree picture, negative 30 degrees going down. All right, enough of that. You got a couple left you could do. Coterminal. That's a fancy way of saying that an angle can have many different names. Because in this case here, if you think about being coterminal, let me just look at this 90 degrees they wrote. If I open up from here, this initial side, I open up to 90 degrees, which, by the way, is pi over 2. You may as well memorize it. I'll talk more about it later. But think about something here. What if I went around the circle more than one time? Watch this. Let me start here on the initial side. Here I go. Go around, go around, go around, and stop right here. Well, because you stopped here, that angle has the same initial side and the same terminal side. It makes the same picture. I mean, in reality, you don't know how many times an angle goes. So what could happen is, let me see what kind of work they want us to do. Angles in standard position with the same terminal side, they're called coterminal angles. Just determine if these are coterminal. Well, it's kind of hard to look at those numbers. I will draw a 305-degree angle on this set of axes. So let's try it. Here's my initial side, opening up, 90 degrees. Another 90 makes it 180. Another 90 makes it 270. Another 90 would take me to 360. That's too far. I only want 305. So let me back up. Let's see how many degrees I need to go into this quadrant 4. So I'll do this, 360 degrees, which was too much, minus 305 is a 55-degree angle. So that means I need to just go in a little bit right here, and there's my angle going to terminate there. That would be a total 305 degrees. 305 degrees was all of that, which that implies this leftover part here is the 55 degrees. Okay, so this red angle that I opened up, I'm going to now trace it in black. Here goes all the way to 305. Okay, now let's talk about the negative 55-degree angle. Negative 55 means I start with my initial side here at 0, and I go clockwise down 55 degrees. There it is. So that angle terminates here. Well, interesting question. This is my negative 55 degrees here, which looks exactly like the 55 degrees that I wrote here. So are they coterminal? They have the same terminal side, so they are coterminal. Yes. When I move over to another one, let's try 30 degrees and negative 170 degrees. I'll do them on separate axes. 30 degrees. Let me do that one. Start at 0 here and open up 30 degrees. Now remember, between here and here are 90 degrees. 90 is too many. I need 1/3 of that. So 1/3 would just be opening up to about here. And I draw my other ray. There's my 30 degrees. Looks pretty good. Now let's look at the negative 170 degrees. Well, I start with my leg on the 0 degrees, and now I'm going to open clockwise, the way the clock goes. Here goes. Here's negative 90. Keep going. Another negative 90 makes it a negative 180. Whoops, that's too many. I only want a negative 170. So let me back up. I'm only going to go up to here. And I go to the origin and I draw the leg out. There it is. That would be a negative 170 degrees. Look at the terminal side. This opened up, terminated up here in quadrant 1. This opened down clockwise and opens up in quadrant 3. Are these terminal sides identically in the same place? You're right. No. They're not coterminal. All right, let me do one more for fun. Not that this is fun. This sometimes gets hard. Let's do a pi over 4 radians. And I'm going to show you my trick. Here's my trick. If I go all the way to the first line, that's 90 degrees. And if I cut that in half, well, let me first do this. Let me keep going. That's 180 degrees. But remember, it also is called pi radians. This is pi. Well, if I go to 90 degrees and I stop up here, that would be half of pi. So we call that pi over 2, which is 90 degrees. If I only go up halfway to 90 and stop right here, that angle is a 45 degree. But because it's 1/2 of 90, look at this. I can cut the other 90 in half as well. So this is a pi cut in 4 pieces. 1, 2, 3, 4. So what's my whole point? My whole point is this. Whoop. Come on. One more erase. Can't get it. There it is. Pi over 4 is 1/4 of the way to 180 degrees. This is pi over 4, which is the same as 45 degrees. So there's my one angle. Now, let's do a -9 pi over 4, going clockwise this way. Well, this would be a negative pi over 4. This would be 2 pi over 4 negative. This would be the 3 pi over 4. This is 4 pi over 4. By the way, -4 pi over 4 is the same thing as a negative pi. Negative pi. So there's 4. Here's 5. Here's 6. Here's 7. Here's 8. And here I go, finishing it up, 9. -9 pi over 4. So the question I would ask you is, if this terminates in quadrant 4, and I'm going to count them again. Here goes. I'm going to count them again. 1, 2, 3, 4, 5, 6, 7, 8. One more again. There's your -9 pi over 4. Does that terminate in the same place as pi over 4 did? No. All right, so you can do that last one there. Let's talk about the next thing. Give 2 coterminal angles for each angle that is given, all right? They said let one be positive and one be negative. Well, here's what I'm going to do. If I want to draw a 150-degree angle in the positive direction, check it out. Start at 0, 90, 180 is too much, so I'll back up and only do 90 plus, let's see, 150 minus 90 is 60 degrees. So go 60 degrees more, there it is. There's 150, okay? Now, I want to draw a negative, so 150 is my positive. I want to have an angle that ends up in the same place, but it's a negative answer. So I'm going to draw this way to the same location. So we need to figure out what that was, okay? Well, if I go negative, here's -90. Here's a -180. All I need to know is to figure out what was this distance here. Well, I probably did the work for you up here when I did 150 minus 90 was 60 degrees. That told me that this angle right here was, let's see, 150 minus 90. This was a 60 degrees. So this must be 30 degrees because they have to add up to 90. So this has to be a 30 degrees. So let's try it again.
negative 90, negative 180. 180 plus 30 is 210. That's a negative 210 angle. So these two angles, one positive, one negative, are considered coterminal. And they are difficult to do sometimes, but let's try one more here. They gave me a positive 265. Let's find where that is. Positive 90, positive 180, positive 270. Well, that's too many, so I'll back it up. 270 was 5 degrees more than I needed. So I will only open it up to here, there. That would be a positive 265 degrees. That implies that this little distance here was only another 5 degrees that's in there. I might need to know that number. So let's do the negative angle. Let's go the other way. I want to end up in the same exact quadrant number 3. So I want to end up right here. There's the side. The picture looks the same, but I'm not measuring it the same way. I'm measuring it negative. So this is a negative 90 degrees right here. But remember, I said this was a 5 degree distance. So if I add 5 more degrees to the 90, make it negative 5, that adds up to a negative 95 degrees. There it is. Negative 95 degrees is coterminal with the 265. Now, it seemed like a lot of fun, right? Let's do another one. Pi over 12. That's probably kind of difficult because to draw it, I need to realize that pi, which stands for 180 degrees, has to be divided by 12. So that's going to be kind of hard to do. So if I just cut them up into like one piece and one piece, that's 4. So technically I'd have to divide each of these by 3. So it's going to be kind of hard to get 3 in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. Pi over 12 is very small. So if I want a pi over 12, it's this angle right here. Pi over 12. It's 180 degrees divided by 12 pieces. So it's not very, it's more difficult than I wanted it to be. But let me draw it again. I'm not going to do all the tick marks. Hopefully you take my word for it. That pi over 12 is very, very small. And I go up just a little bit. We'll call that pi over 12. Well, if I go all the way in the negative answer now, if I will go negative answer, then what would that become? Well, think about it. All of this would have been 12 pieces out of 12. This would have been adding 6 more, so you're up to 18. I guess you could also look at it that the whole circle would have to have 24 different angles in it. 12 down here, a lot of them, and then almost 12 at the top except for this one. So I'm going to say that it would be a negative 11, no, not 11, a negative 23 pi out of 12. Because they have 12 plus 11 more to get to this angle. That's probably the hardest one to think of. Pi over 12 and a negative 23 pi out of 12. That's the hardest one. probably star it. You might want to talk about that in class. All right, let's see where we're at in this set of notes.
And the next one, online.
That set of notes is done. So we're going to call that a day of notes for Wednesday. And sometime in the evening, you want to look for this lesson where I move on, because after this lesson is and posting it. So you'll have homework. Your homework will be to do this set of notes at home on Wednesday night or Thursday before you come to school on Friday. Over and out. Homework is tomorrow. So I will be doing this lesson